In the name of God, the all-compassionate, the all-merciful. In this video, I wanted to talk about the composites. Actually, the composites, composite plate with a hole, and I wanted to model the stress concentration in this kind of plate. Before modeling, I wanted to explain more about composites and other features about these materials. So here I want to define composites. Composites are the material that have more than one parts. The first important part is fiber, and the second important part of composites are matrix. And composites can make more than two or more than two parts, but they have the same feature that fiber and matrix are important ones. There are many types of composites, but I wanted to talk about this kind of classification of these materials. The first one is fibers or long fibers. The example for this type of composites is carbon epoxy or glass epoxy. These are classified in this group. The second one is short fibers like clay. These are made of some short fiber into the matrix. And the last one is particulates like concrete. Composites. In this video, I wanted to talk about the first group and model the composite that is classified in this group. This kind of composites can made of just one ply or made of multiple ply. The first group is called lamina and the second one is called laminate. In these materials, the composites, if the composite is lamina, there is such a specific kind of equations, and if it is in laminates, the equation for this material is different. If the composite is lamina, the equation is here like that, and we can join the force and strain by Q, the Q matrix, and you can see here the element of this matrix. E1 and also E2 and Poisson ratio and other parameters, and also G12. If we have these constants E1, E2 and also G12 and Poisson ratio, we can calculate this matrix. But in laminate, the equation is different, and the matrix is changed into this big one, and it is so larger than the previous one, but we can calculate it easily, and there is no problem. And I wanted to talk about more about these elements of this matrix. This one is the force part, and this one is strain or curvatures. Here is strain and here is curvature, and here is axial force, and here is moments. And this matrix connects this one to this one. But I wanted to talk about how to calculate any elements that is available here. So I come here, and in this slide, the more explanations about this matrix is available, and we can understand more the effect of each part, each element, and how they can change the composites situation. For example, A12 shows the deformation at this direction when the force is located in this direction, the first axis, and the deformation is second axis. And any part of this matrix shows different behavior of the composite after the specific force, and we can explain any element, and here it is shown, and here there is simplified equations of the larger matrix. This one n nx and y y and xy and xy, and this we can here see more easier explanation here. How to calculate A, B, and D elements? These are the equations of these elements A, B, and D, and we can calculate it easily. And here it is shown the Z and ZK minus 1. Here we can understand more. The Cij shows any part of the element of this matrix. We should calculate this red matrix for each layer and multiply by zk minus zk minus 1, and then the summation of each layer's matrix shows the A1. And also zk minus zk minus 1 is also the thickness of the specific layer, and we can show it by this term. And also in B and D there is some equations that is similar to that the A1, but this part is different, and we can calculate it and again do it. But there is no it is not necessary to calculate it, and we can use some websites to do it more easily. Here I have a link. We can come here and go to the website. I wanna to type the link here. If you have some website, you can here come and find the equations and actually the elements. So you can do it and test it. Go to this website and enter your values, and then we can calculate A, B, and D for each matrix, and it is so easy when we come here in this website. So in this video I wanted to talk about the stress concentration in composite plates with hole. But before the main model, I wanted to talk about the plate with a hole and stress concentration. First of all, in isotropic plate, we can see here that the values of stress concentration in different diameter radius divided by this distance, and there are different values in different R divided by D values, and actually K shows the values of stress concentration. You can here see that there is a high value of stress at the edge of the hole. So I wanted to talk about it in anisotropic plate. Here you can see that orthotropic plate there is different layup here, here, and here, and the values of stress concentration is different actually. And you can see that the photoelasticity of the plate, boron epoxy plate, and also the values is different, the strain value is different, and we can calculate it by some relations and actually model it by ABAQUS. Here I wanted to model it. So in this example, I wanted to model the plate with 80 centimeter, the square plate with 80 centimeter dimension, and actually the hole with 5.6 centimeter diameter, and the thickness of this plate is actually 1 centimeter. Before modeling, I have calculated the values for the boron epoxy, the E11, E22, and the Poisson ratio, and G12 for this material is here, and by these relations we can calculate it. And actually, I've calculated this matrix and inversed it to calculate the values in the reference coordinates. So here, just because the stress that I mean tensile forces is works in this matrix, and B matrix is not important because this coupling of axial and bending effects, and there isn't any bending effects here. And D1 is the D matrix is actually for bending effect, and so there is no need to calculate this matrix. So here I have calculated A matrix I mean, and inversed it to calculate the the matrix that is changed the force into strain. That is the reverse of the matrix A. So here I've calculated and inversed the values so we can find it here. And then I wanted to enter the values and actually start the modeling. So here I come in part. I want to draw draw my shape here. I wanted to enter the values here, and then the values we can draw a hole. The 5.6 is the diameter, so the radius is 2.8. I come here, and then the modeling is the shape is completed. Here I wanted to model my material. I choose engineering constants, and actually the values is in centimeter, but we can enter the values in kilogram divided by centimeter. But I want to suppose the values is in millimeter, so it is so easier to change the units. So the dimension is actually 80 millimeter and 5.6 millimeter. It is so easier for me to model, but it is, there is no difference to the values that is entered, just the unit conversion needs, and we can do it easily here. So I wanted to enter each values. Actually we should multiply the values by E3. So here I should do that, E3. Alright, the action completed. So I wanted to define a section we can actually choose plane stress or strain Neufren in the result in this actually modeling. And actually I wanted to define orientation. I click here, coordinate system axis 3. It is okay. In the x direction this axis 1, and in y direction it is axis 2. So I click here, all the setting is okay. Actually I want to assemble, and actually step, no need, don't change needs here. I come here in load. I wanted to define the load before the defining the boundary conditions, that in this edge all the boundary condition is closed, and here just the load in y direction is applied. So I come here and choose symmetry and axisymmetry and choose the last one. Alright, here I want to define the load, actually the pressure here, and to understand easier, it is better to define one value to calculate it easier, the stress concentration easier. So here in mesh, it is I want to mesh my part, but before meshing it is important, the seat side is size is so important, and I want to choose the right value to see the better results. So I choose 0.05 for the local seeds near the hole where there is a stress concentration. Actually the global size is 2, and I wanted to choose the mesh type. The plane strain is okay. So then I want to mesh. Here meshing will be occurred, and actually alright, I come to job and define a job. Before submitting I want to check the data if it is okay or not, and then I wanted to submit my job. Alright, there is no problem here, so we can submit it easily here. After submitting we can see the results and the stress concentration. Before visiting the result, I want to show the values. In this table you can see the stress concentration values in different layout. In my material, my model, the materials layout is here like that, and the value, the predicted value is 5.8, and also the measured value is 4.82. And I want to see whether the value of my analysis is closer to this value or to that value. So I want to visit the result. Here we can see the value. Actually we should come in the Z direction. The value is really 5.28, so we can compare. It is closer to the measured value, the experimental value, but we can if we choose the smaller meshes, we can go closer to the this predicted value. Predicted value is calculated by some relations, but we can go closer to this value. But in this modeling we see 5.28, and you can see it easily here. We can go closer. Here there is some stress concentration. The value is 5.28. If you change, for example, the element type, the value will be different. For example, the reduced integration changes the final value. We can see here the type of element, the type of meshing technique, or the mesh size. Every parameter can change the final value of the stress concentration actually. And I want to explain that the force that is applied is 1, and the stress on the hole shows the value that is multiplied the force. If it is 5.8, it means that the force is multiplied this 5 times. So you can here see that I've changed it to the reduced integration type, and the value is changed into 4.82, and it is closer. It is the exact value that is measured in experiments. So the element type is so important, and by changing the element type you can have the different results.